When you are working into data science and data analytics, you will be dealing with large number of data in different columns and rows. When dealing with numbers, you want to perform the calculations quite fast. And that's where the Numpy library comes in. Numpy is the backbone for many of the scientific and numerical computing libraries in Python. It is also used in Pandas package, which is one of the most popular package for data science. There are several reasons why you should be learning Numpy. First, because it works close to the hardware, that's why it is super fast in performing computations on numerical data. It's also widely used in scientific computations, so learning this will give you an edge if you are working into scientific field. To give you a brief idea about Numpy, the basic data structure in Numpy is Numpy arrays. It is faster than Python container data types like list or tuple. We will also explore the comparison between Numpy arrays and Python list in this video. In order to use Numpy, we first have to import Numpy library. We can write import Numpy as np. This alias np is the convention among Python developers, and whenever you see np, it refers to Numpy. You don't want to write Numpy and then the function name because you will be writing Numpy multiple times, and that's why you want a shorter syntax for it. So now with this import, we can write np.some function from the Numpy package. There are multiple ways to create Numpy arrays. We can convert Python sequence data type into Numpy array by using np.array function. So let's create our first ever Numpy array. Numpy array A equals np.array, and this array function from Numpy module will take any sequence. So let's pass a list of 3 numbers, 1, 2 and 3. Let's also print this array. You can see that it has created an array with 3 elements. If we want to check the data type of this array, I can type A, and it gives numpy.nd array. Here this nd array means n-dimensional array. It can be multi-dimensional array or it can be a single dimensional array like this. If I want to create multi-dimensional array, then I can pass a nested list. Let's create 2-dimensional array using np.array, and in this array function I can pass a nested list where the first list is going to have elements 1, 2 and 3, and my second list has the elements 4, 5 and 6. If I print this matrix array, then it's going to print my array. Similarly, I can create a 3D array like this. In this case, I have to pass the nested arrays 0, 1, 2, 3, 4, 5, 6, 7, 8, and then in my outer nested array, I can pass another array 1, 2, 3, 4, 5, 6, 7, 8 and 9. Let's print this array. We can also check the dimension of these arrays using ndim attribute. So Numpy arrays have attributes and methods on them. If we take a look at the dimension of our first array, a.ndim, it has only one dimension. So if we take a look at our array, it has only one nested list. Our matrix has 2 nested lists, and our 3D array has 3 level deep nested list. So let's check the matrix dimension. It returns 2. If I check the same for my 3D array, it returns 3. To give you a brief idea about these dimensions, one-dimensional array is called a vector, two-dimensional array is called a matrix, and more than two dimensions are called tensor. That's how we get the TensorFlow library, which is one of the most popular libraries for creating deep learning models. If we want to create a NumPy array from a sequence, then we can use aRange function. This aRange function is very similar to what we have in Python using range function. Array1 equals np.arange, and if I pass 10, it will create an array with elements 0 to 9. Let's print this, and you can see that we have elements from 0 to 9. If I want to check how many rows and columns this array has, then I can use array1.shape. This shape attribute gives a tuple with number of rows and number of columns. In this case, we only have one dimension, and that's why it returns 10. Similarly, if I check the shape for my matrix, then it should be 2 by 3. And for my 3D array, let me print this. Our 3D array has two inner matrices, and both of them are 3 by 3. So if I type array3d.shape, it should return 2 by 3 by 3. We can also find how many elements our array contains using size attribute. Array1.size. Remember, this is the array we created using aRange function. It has 10 elements. If I check the same for my matrix array, it has 6 elements, and similarly for my 3D array, it has 18 elements. In Jupyter Notebook, there is a trick to check the documentation of a specific function. If I type np.arange and if I press Shift and Tab, it will open up a docstring for this specific function. If I take a look at this documentation, then you can see that this function takes a start value, a stop value, and a step value. It also takes the D type. This is the data type for the array we want to create. And if we take a look at these first three arguments, this looks very similar to what we have in Python for a range function. So let's try these additional arguments. If I pass the values 5 and 10, so in this case the start value is going to be 5 and the stop value is going to be 10. It creates our array with elements 5 to 9. Let's specify the step value as well. np.arange 1, 10, and with a step of 2. And you can see we have all the elements which are separated from each other by value 2. Similarly, if I want to create an array with elements between two numbers, then I can use linspace function. This function will create an array element which are evenly separated from each other. Let's try this. np.linspace, and I'm passing these three arguments. The first argument is the first element value, and the second argument is the last element value. And in between we should have total 6 elements. So our created array, array2, will have total of 6 elements. Let's print this. You can see all the elements are separated from each other by a value of 1. Our first element is 0 and the last element is the value 5. If we want to create an array with all the elements as 1, then we can use the built-in function once, np.once, and this function takes the shape of the array we want to create. Let's create a 3 by 3 array. You can see that all the elements have the value 1. Here all the elements have this trailing dot. This means all these values are of floating point value. We will learn more about these data types as we go along this video. If we want to create all the elements with a value of 0, then we can use zeros function. Zeros equals np.zeros, and this also takes the shape of the array we want to create, and it creates all the elements with a value of 0. If I want to create an identity matrix, then I can use I function. One quality of identity matrix is that it will always have the same number of rows as the number of columns. So I only have to specify one value. Let's create a 3 by 3 identity matrix, and it has all the elements in the diagonal of the array as 1. By the way, I may be using matrix and array interchangeably. If I want to create a diagonal array, I can use diag function, and this diagonal array will have some elements in the diagonal of this array. Those elements can be specified by passing a list into this function. So let's pass the values 1, 2, and 3. And you can see that the diagonal elements have those values. Now we are not limited to creating arrays by passing some values. Sometimes we want to create a huge array and we don't want to pass all the elements manually. So in that case, we can make use of the random module from this Numpy package. I can write np.random.rand and I can pass any value into it. This will create an array with 4 elements. In this case, it has created elements which are randomly distributed, and to be precise, it's a uniformly distributed elements between 0 and 1. If we want to create an array with elements distributed using standard normal distribution or Gaussian distribution, then we can use randn function. np.random.randn with 4 elements. If I want to create an array with integer values, then I can use the randint function. np.random.randint. We want a number between 1 and 10. This will actually create a single number. Let me print this. But if we want an array, we can also specify an additional attribute, size. Let's create this random array, np.random.randint. We want elements between 5 and 10, and let's also specify the keyword argument size with 4 elements. Let's print this random array. You can notice that all the elements are between the values 5 and 10. If I want to create a 2-dimensional array of a specific size, then I can specify that size into this size attribute. Let me create a 2-dimensional array, np.random.randint, between 5 and 10 with a size of 3, 4. If I print this array, you can see that it has created 3 by 4 array. This is very useful because we don't have to specify the elements manually. We can create an array of any size. We just have to specify the size we want to create. If I check the shape of this array, it has 3 rows and 4 columns. If I want to create an array of floating point values, then I can also use random.random and I can specify the shape in this tuple. Let's create 2 by 2 matrix, and it creates a 2 by 2 matrix with all the elements between 0 and 1. Now talking about Numpy random numbers, these numbers are actually pseudo-random numbers. This means they are not actually random, but they appear to be random. We can set a seed, and that will make sure that every time we run that cell, it will generate the same numbers. If I write np.random.seed and set some value, let me set this to 1. Now if I try to run np.random.randint up to the value 10 and size of 2 by 3. If I execute this cell, it generates these numbers. But if I try to rerun this cell, then it will still generate the same numbers. No matter how many times you run this cell, as long as this seed value is the same, it will generate the same numbers. This can be very useful when you want to experiment with the data and you want to generate the same numbers every time you run the experiment. You can simply set this seed and it will have the same values all the time. Now this randint function allows us to create multidimensional arrays quite easily. If I want to create a 4-dimensional array, I can simply write np.random.randint. I want to generate numbers up to value 10 and I can specify the size as 2, 3, 3 and 4. Typing all these elements manually will be very difficult, but with randint function we can generate such large arrays quite easily. If I check the shape of this array, then it will have the values 2, 3, 3, 4. If I want to see how many elements are available in this array, I can write the size attribute. I can also verify this value by multiplying all the elements of shape tuple 2, 3, 3 and 4. It equals 72. Now let's compare the performance between the Python data structure and the Numpy data structure. In Python, if we want to transform a list into another list, we can use list comprehension. So let's say I have a list with elements up to 10,000 and I want to convert those numbers into double their value. Then I can do that using I multiplied by 2 for I in range 10,000. This way I can transform my original list into another list. My new list will have the value which is double the value of original list. In Jupyter, we can verify the performance of this operation by using the timeit magic function. If you don't know what magic functions are, then those are simple functions we can write using $sign and then the function name. I can write timeit and it will perform this execution for some number of times and then it will calculate the average time taken by this operation. So here we are checking the Python performance. If I want to perform the same operation using Numpy array, then I can use np.arange function. This will generate the numbers between 0 to 10,000 and then I can multiply all the numbers by simply multiplying this array. Let's verify the operation time, and if I execute this, it will perform all these operations and then actually give us the duration it took to perform these operations. So here we have the result for the first operation. So if we take a look at this, it executed this command for 7 times and it calculated the average and it turns out to be 1.24 millisecond. For Numpy arrays, it took around 31 microseconds. So Numpy is almost 100 times faster than Python equivalent list. So this gives us a rough idea about how performant the Numpy arrays are. Now let's move on to the new topic. Let's learn about the data types of Numpy arrays. In Numpy, we have data types just like Python. We can create an array using np.arange up to value 10. And if we take a look at this all appears to be integer values, but we can verify the data type by typing a.dtype attribute. It returns int 32. Similarly, if I create another array with all the elements as ones, np.ones 3 by 3, here you can see a trailing dot after all the numbers. We can verify the data type using ones.dtype. I can also cast this array into integer array using asType method. Ones.asType of integer, and it will convert the original array into integer data type. Now NumPy arrays are not limited to number data types. We can also create arrays including data values of string as well as Boolean data types. So I can also convert this ones array into string data type like this. If I want to create an array of string data type, then I can create them like this, np.array, and I can pass any value in here. Let me pass some city names: Bombay, New Delhi, and New York. This creates a NumPy array of string data types. Similarly, we can also create an array of complex data types, as well as we can create an array of Boolean data types. Now let's learn about indexing operation on NumPy arrays. Let me create a new heading, indexing. Indexing operations are very similar to how we index Python sequence data types. Indexes start from 0. Let's revise our understanding of Python indexing. If I have numbers list with elements 1 to 5, if I check for numbers at index position 2, then it's going to return the value from this index position 2. This is the 0 index and this is the index number 2. So it returns 3. For NumPy arrays, we can use the same kind of indexing operation. In this case, I'm creating elements between 1 and 11. If I print this array, it has elements from 1 to 10. If I check the shape of this array, it has 10 elements. And if I check the element value at index position 2, then it returns 3. If I want to get elements from multiple index positions, then I can pass a list into this indexing operation. So let's say I want the elements from index position 3 and 5, then I can write like this. Here I can pass a list with index positions 3 and 5. It gives me an array with element values from the index position 3 and 5. For multidimensional arrays, indexing becomes quite interesting. Let me create a multidimensional array for us to verify that operation. I'm going to use randint function, and let's create elements between 1 and 10 with a size of 3 by 3. Let me print this array. So here we have two-dimensional array. If I check the shape, it has 3 rows and 3 columns. If I want to get the element from this middle value, then I can specify that using row number 1, and column number is also going to be 1. So I can write it like this. First I have to specify the row number, which is 1, then comma, and I can specify the column number 1, and it gives me this middle value. So this way we can also index any element from this multidimensional array. If I create a 3-dimensional array, np.random.randint with values between 1 and 50, and let's create the size of, 3 by 3 by 2. Let me print this array. This creates a 3 by 3 by 2 array. Now let's say I want the element from this, then it's going to be from the second nested array, which can be referenced by the index position 1. And I'm looking at row number with index position 2, and it has the column index of 1. So I can write B1, 2, 1, and I get back the value 9. So this way we can also index multiple dimensions using this indexing operation. Now let's look at the slicing operation. Slicing operation is also very similar to Python slicing operation, but with multidimensional arrays, this becomes a little bit challenging. Let's first recall Python slicing operation. We have this numbers list, which is simple Python list. If I want the elements from index position 3 up to the end of the list, then I can write like this. And it gives the last 2 elements. Similarly, I can index like this as well, where I can specify the stop index position. Now let me go back to my array. If I want all the elements from this first row, then I can write A at row number 0. And here I want all the elements, that's why I don't have to specify the column index position. And it returns the first row elements in the form of NumPy array. If I want the first 2 rows with all the values from all the columns, I can also perform the same operation using A 0, 1, and it gives the same array. If I want all the rows from index position 1 up to the end of the rows, then I can write A 1, and it will give me last 2 rows. If I want to create an array which has elements from row number 1 onwards and from column number 1 onwards, then I can write A 1, and then we specify the column values as 1, It will give me the last 4 elements, which are these 2 and these 2. So this way we can get the slices from the original array. We can choose any subsection of the array we want. This way we can also modify the original array. So if I write A 2, this means it will select only the last row. And if I want to set all the values from the original array to a value of 1, then I can do that like this. Let's check the original array. And you can see the original array has now the last row with elements 1. Let's go back to our 3-dimensional array B. It has these values. Now let's say I want the elements from these 2 rows. Then I can write B. I want the second nested list, index position 1. I want all the values from row number 1 onwards. And I want all the column values. So it's going to be 0, and it will give me those 4 elements. We can also select elements based on some condition. Let me recreate our array with 10 elements. Now let's say I want to select all the even numbers, then I can write it like this: A modulo 2 equals 0. This will make sure to select only those values which are even. If I want to modify all the even numbers into value 1, then I can do that like this. Here all the even numbers have been modified to a value of 1. The interesting fact about slicing operation is that it creates a view on the original NumPy array. That means if we modify the view, it will actually modify the original array. Let me show you an example of that. Let me create an array with elements 1 to 5. If I print this array, it has 5 elements. Similarly, if I create a new array, which is actually a view created from the original array between these two indices, then it has these values. If I modify this array 2 at index position 0 to a value of 30, then array 2 has been modified. But if I check array 1, then you can see that array 1 has also been modified. These two arrays are actually sharing the memory location, and we can confirm that by using this shares memory method. I can pass array 1 and array 2 in this function, and it returns true. That means these two arrays are actually sharing the memory location. If I want to avoid having this kind of side effect, then I can create a brand new array using a copy method. Let me recreate our array 1 np.array with elements 1 to 5. Now if I try to create a copy, array 3 equals array 1 between index position 2 and 4, and here I'm using the copy method. This will make sure that it will create a brand new copy of this array 3. So it will not be sharing the memory location with array 1. If I modify this array 3's 0 index position to 30, then it has modified this array, but our original array is not modified. Let's look at some of the common operations we can perform on NumPy arrays. We can perform scalar addition by adding a scalar value into an array. Let me create a new array with range 5. So it will create elements between 0 to 4. Now I can add a scalar value like this, and it will add that value 1 into all the elements of this array A. So it creates a new array with elements 1 to 5. Our original array had the values from 0 to 4, and 1 has been added to all the elements of this array. I can raise value of all the elements to the power of 2 using this operation. Similarly, I can multiply all the elements by a value of 2, and I can divide all the elements by a value of 2. When we perform similar operations on two NumPy arrays, then actually it will try to perform element-wise operations. Let me create a new array np.array with elements 5, 6, 7, 8 and 9. Our original array has the elements 0 to 4. Now if I perform b minus a, it will perform element-wise subtraction between these two arrays. So it will perform 5 minus 0, 6 minus 1, 7 minus 2, and so on. Similarly, if I try to perform the multiplication between these two arrays, it will perform the element-wise multiplication of all the elements. And I can also perform the addition. If the size of these two arrays do not match, then it can throw a value error. Let me create a brand new array C with values 10, 11 and 12. Now if I try to perform A plus C, then it's going to throw a value error, and you can see the error message: operands could not be broadcast together with shapes 5 and 3. So in order to perform these arithmetic operations between these two arrays, their shape should match. We will learn more about this term broadcast towards the end of the video. But let's move on with few other operations. If you have studied linear algebra, then you might be familiar with the dot product of two arrays. In order to perform the dot product between two arrays, the number of columns from the first array should match the number of rows on the second array. Here I'm going to set a seed np.random.seed to a value of 1, and let me create my first array np.random.randint up to 5 and with a size of 3 by 2. Let me print this array. Now let me create some separation between my dot product and this array. Here I'm going to create another array np.random.randint up to the value of 2 with a size of 2 by 3. Now the number of columns on this array should match the number of rows on the second array. Then only we can perform the dot product between those two arrays. Let me print this one, and here I am going to perform a1 dot a2. If I execute, it returns this new array of size 3 by 3. So how is this dot product calculated? Let me take you to a diagram where I can show you how this dot product is calculated. So if we want to find the value at this index position, then this value is calculated using the first row and the first column of the second row. So it will perform 3 multiplied by 0 plus 4 multiplied by 1. Similarly, if I want to calculate this value, then it performs the same operation with the first row of the first array and the second column of the second array. So it performs 3 multiplied by 1 plus 4 multiplied by 1. And that's how we get all the values in this array. Now, if we want to find a transpose of a matrix, then we can find it by converting all the elements on a row into a column. Transposing a matrix means changing the row into respective column. Let me get back to my array A1. Here I have 2 columns and 3 rows. If I try to transpose this array, it would look like this. So the first row has been converted into first column, and the second row is converted into second column, and so on. I could perform the same operation using np.transpose method, and I can pass the array I want to transpose. Let me go back to my previous array A, which has numbers from 0 to 4, and I had also created an array B with elements 5 to 9. Now if I want to compare these two array elements, then I can compare them like this: A less than B. Then it will perform element wise comparison. So 5 is less than 0, that's why it returns true. 6 is also less than 1, then it returns true. And this way it performs all the element wise logical operation. If I create a brand new array A2 equals np.array with the element values 0 to 4, then I can also compare this array with the array A. A equals A2, then it returns all the values as true. But if I want to check if complete array is equal to another array, then I can write np.array equal, and I can pass those two arrays as argument into this function. It returns true. If I check the same operation with my array B, then it's going to return false. Similarly, there are methods to perform logical OR operation and logical AND operation between all the elements of two arrays. We can also find a sine or cosine of all the elements from an array using np.sine and np.cos method. To find logarithm of all the elements, we can use the log method from Numpy module. Now let's take a look at some of the statistical measures we can find using Numpy. If I take a look at np.sum of all the elements from my array A, then it returns 10. I can perform the same operation using a.sum method. Similarly, if I want to find the min, I can write np.min of A, and to find max, I can write np.max. Now, if I take a look at my array, it has elements 0 to 4. Let's say I want to find the index position where the minimum value occurs, then in that case I can write argmin of array A. And in this case, my minimum value occurs at index position 0. If I check np.argmax in my array A, then it returns 4. This is the index position where the maximum value occurs. Numpy arrays have interesting concept of axes. You might be familiar with axes from mathematics, but in this case the axes have the values 0 and 1. If I create an array of 3 by 3, then it will have 3 rows and 3 columns. Now if I want to take a look at axis 0, then this is defined in the row direction. Where all the rows are increasing in that direction, the axis 0 is defined. Axis 1 is defined along the column direction, so this is where the axis 1 is defined. If I want to perform summation, I can also specify the axis along which I want to perform the addition operation. If I perform the addition operation along the axis 0, then it will return these values. So it performs 1 plus 3 plus 1, and that value will be inserted into this first index position. Similarly, it calculates these two values. If I perform the same sum operation along the axis 1, then it returns this array. So let's take a look at a practical demo of this sum operation. Let me create a brand new array, np.array, and this is going to be 2 by 3 array with elements 1, 2 and 3, and my second row has the elements 3, 2 and 1. Let me print this array. If I perform np.sum of this array along the axis 0, then it's going to return 4, 4 and 4. If I perform the same operation along the axis 1, then it returns the values 6 and 6. If I want to find the mean value from this array elements, then I can write a.mean, or I can also write np.mean of array A. Similarly, if I want to find the median value, I can write np.median of A. To find the variance, I can write this method of A, and I get the variance of this array elements. To find the standard deviation, I can use this method, and it returns the standard deviation of all the elements from this array. We could also find the mean along a specific axis like this, np.mean of our array along the axis 1. Now let's learn about how we can sort the elements of an array. Let me create a new array which is not sorted at all, np.array with elements 4, 3 and 5. These are not sorted, and my second row has the elements 9, 3 and 2. Now if I want to sort these elements, I can write it like this, np.sort this array, and it will actually sort the elements row wise. So it sorts these 3 elements and organizes them into specific order for the first row, Then it sorts this row and arranges them into ascending order. If I want to perform the same operation, I can also specify the axis as 1. np.sort and axis equals 1. Then it gives the same result. But if I want to sort elements column wise, then I can also specify np.sort array axis equals 0. It will arrange elements along the axis 0. Now let's take a look at the concept of broadcasting. Let me go back to slides. Broadcasting is a technique which allows us to perform element-wise operations on arrays which can have different shapes. When operating on arrays, Numpy compares their shapes element-wise. If both the arrays have the same shape, then we can easily perform element-wise operations. However, if one of the array has a different shape, then it becomes tricky. In order to perform broadcasting operation, Numpy verifies the dimensions and checks if they are compatible with each other. If one of the dimension is 1, then it can be broadcasted to match the dimension of the other array. This diagram shows how it can be performed. So if I try to perform element-wise addition of a 3x3 matrix with a vector, then these elements will be broadcasted and it will create another 3x3 array by repeating this specific row. So as a result, we get this array. The same operation can also be performed if we have two vectors. So here I have this vector with 3 rows and 1 column, and I'm trying to do element-wise summation of this vector with another vector which has only 1 row and 3 columns. So in this case, this array will be broadcasted into 3 columns and this second array will be broadcasted into 3 rows. Finally, we get this result. Let's perform these operations in practical demo. So here I'm trying to create an array np.ones and I want to create a 3x2 array. Let me print this array. So I have 3 rows and 2 columns. Let me create another array with elements 4 and 3. So this is going to be my another array and it has only 1 row and 2 columns. Now if I try to perform array 1 plus array 2, then you can see that it returns these values. So this row is actually broadcasted into 3 rows. It creates 2 extra rows with the same values. Similarly, if I create array 3 with np.array, I'm creating single column 1 to 3. If I transpose this, then it is going to return me a single column. If I perform this transpose and sum it with the elements from array 1, then it is going to broadcast these 3 elements into another column and then perform the element-wise summation with all the elements from array 1. Similarly, we can also perform other arithmetic operations as well as comparison operations between 2 arrays. Now let's say I have an array 1 with elements 1, 2 and 3. If I want to repeat these elements and create the new rows, I can use the tile function from Numpy module. I can write np.tile and I want to repeat this array 1 elements. I want to create a 3x1 array. If I print this array, then you can see that it has repeated those 3 elements into 3 rows. If I try to perform the same operation and try to create an array of 3 by 2, then it will create 3 rows with all the elements. Sometimes we may need to modify the shape of an array. For that we need some shape manipulation methods. So let's learn about those. When we want to perform operation between two arrays, those two arrays should have similar shape or they should be compatible with each other. Then only we can perform those operations. So in these cases, we need to manipulate their shape. Let's see how we can do that. Mainly there are two main methods. One is reshape and another one is resize. Let's take a look at their example. Let me create an array, and in this case I'm going to create an array by passing nested array using np.arange. np.arange with elements 1 to 5 and np.arange with elements 10 to 14. Let me print this array, and it has created this 2 by 4 array. If I check the shape, it has 2 rows and 4 columns. If I want to flatten this array and create a simple vector with 8 elements, I can use the ravel function. Array.ravel, and it flattens all the elements. It creates new array with first row and then all the elements from the second row. We have seen how we can manipulate this original array and change rows into columns and columns into rows using transpose. So if I perform the transpose operation, it has converted the rows into columns. So this is also one of the techniques to reshape our original array. We can also use reshape to flatten or unflatten an array. Let me try to flatten my original array.ravel. So it should have flattened my array into something like this. Now I can reshape that array and convert it back into my original 2 by 4 array. So this operation returns me the original array. Let me try to reshape a brand new array. Array equals np.arange with elements 12. So it will create an array with 12 elements from 0 to 11. Now I can reshape this array into a 3 by 4 matrix. If I try to reshape into an array which cannot accommodate all the elements, then it is going to throw an error. So if I try to reshape into 2 by 3 array, then it can accommodate only 6 elements. So in this case, it throws a value error. Cannot reshape array of size 12 into shape 2 by 3. I can definitely reshape into 4 by 3 array like this. This reshape operation actually creates a view. So if I create a brand new array, array.reshape as 4 by 3. Now if I take a look at my array 2, it has these 4 rows and 3 columns. If I modify my array 2 at index position 2, 2 to a value of 100, now I can take a look at my array 2. It has value of 100 at that index position. But if I take a look at my original array, then that array has also been modified. This can be a dangerous operation depending on how many times you are referencing the original array. This is where resize operation can be useful. Let's see how we can perform the resizing operation. I'm creating a new array np.arange with 5 elements. Now I can resize this array into any number. So if I write resize to 8 elements, then it will create a vector with 8 elements. If I take a look at my original array, then that array has been modified and 3 new elements have been added. All the new elements have been added with a value of 0. So this way, resize can add extra elements with a default value. We can resize an array only if it's not referenced by some other array. Let me show you what I mean. I'm creating a new array with 6 elements. Now I'm creating a view on top of this array of 2 by 3, and let me also print this array. Now if I try to resize my original array into, let's say, 8 elements, then it's going to throw a value error. Cannot resize an array that references or is referenced by another array in this way. We are referencing that original array into this array2 view, and that's why it cannot resize once we have referenced that array. So in this video, we looked at many functions from this Numpy package. Numpy provides an efficient way to perform operations on numerical data. We saw how we can create NumPy arrays. Then we saw indexing and slicing operations on those NumPy arrays. We saw how we can sort a NumPy array. And we looked at broadcasting technique, which allows us to perform operations on NumPy arrays of different shape. Finally, we looked at how we can modify the shape of our original array.